Welcome back. The topic this week is about what's called a particle hole transformation. And that's something which is going to make life easier for us. And we saw last time, even if we used a diagrammatic representation and we used Wick's generalized theorem, we still end up with many legs or single particle states to take into account. And the normal situation is that we have typically an interaction which is a type of one body, two body, and three body. And that means that the interaction acts on 2 or 3 particles at a time. And then if you have 100 particles and you're calculating an expectation value, the ground state expectation value, you have to also deal with the other 97 particles if you have a 3-body interaction. If you have a 2-body, then you have 98 particles which don't interact. But then you have to look at the contractions between all these. And this becomes pretty messy after some time. And that begs almost for the introduction of another type of creation and annihilation operators. So we can always perform transformations of these operators. And you will see examples of this later as well. But one of the simplest types of transformations is the so-called particle hole transformation. So let's bring that up. Concerning the exercises, I have a new set of exercises which also deals with these basis transformations. And that's also linked to the way we can deal with this creation and annihilation operators with a new basis set. And it's going to be important when we now deal with many-body methods. So we needed something like 4 to 5 weeks to get through some basic formalism, which then will allow us to rephrase a many-body problem in a more compact and efficient way. So what we've done till now is ways of compactifying the equations. So if we look back at what we had last time, and also with the Lipkin model, which was an example of a 4-particle state, when you're calculating the expectation values or transition probabilities with Wick's theorem, you still had to run through all the 4 single particle states and make the contractions. So let's see how we can compactify that. And this is what the particle hole formalism actually promises. So I'm going to do this in 2 steps. So the first step is what you will normally see as the traditional step, where you introduce new operators. Then we are going back to the original operators, but then we have to be a little bit careful with the anti-commutation rules and also the definition of the contractions. So I hope I can baby step you through these different steps here. And I also suggest that we, if you haven't finished the Lipkin model, we can still work on that tomorrow. And because I'm going to use that model as an example of applications of many-body theories. So let's take a look now. When we used Wick's theorem, either in a diagrammatic form or in an algebraic form. So let's now do this in a diagrammatical form. So we would have the states, single particle states, and let's call these alpha 1, alpha 2, alpha 3, up to some alpha n. And then we have an operator, which in this case is a 2-body operator. And then we have the states here again. So we could think of this as a Slater determinant, which is an ansatz for the ground state, and where we have filled all the levels up to the nth single particle state. And then we have to perform the contraction. So clearly, if we have 100 here, this becomes a little bit, how to say, untractable. So this Slater determinant, which you see here, is then represented by this set of creation operators. So we have an A dagger alpha 1, alpha 2, and so on. And all the way up to an A alpha n dagger acting on the vacuum state, the true vacuum state. And this is normally something which we would call an n-particle state. So in the beginning today, I'm just going to give you some definitions, and then you will see how we can then motivate the introduction of a new type of creation and annihilation operators. What we could do now is we could add one particle. And we know that since these are now fermions, if they are bosons, I mean, we can have more than one single particle state, which is filled by more than one particle. So if we add one particle, we would typically have an operator of the type A alpha n plus 1 dagger. And this is now acting on this state, which I also write in a more compact way, like this alpha n. And we want to have a specific ordering. And the type of ordering we want of the single particle states is that 1 is less than 2. So they have a hierarchy here, alpha 1, alpha 2, alpha 3, and up to alpha n. So we have decided upon a specific hierarchy of the single particle states. So since this alpha n plus 1 is now something on top of alpha n, we have to permute the operators. So that means that this state here is now given by some minus, and then we have the sign here. This is the number of permutations which we have to make. And then we will have an A alpha 1, alpha, this is an alpha, alpha 2, alpha n, and alpha n plus 1. This is now an n plus 1 wave function or state. Now, what could have been beneficial now would be to perhaps rewrite this original n particle state as something which we could define as a new vacuum. So what I'm doing now is simply to motivate a more compact notation for a specific type of reference state. So we could also rewrite this one if we want to. This would be given by A alpha 1 dagger, A alpha 2, and then we have all the way up to alpha n dagger, and then A alpha n plus 1 dagger acting on 0. And this is then multiplied with this phase of n. We can do the same thing with a state where we now remove a particle. So we could now think of acting with an operator A, and let's just call this alpha, which now acts on the same state, alpha 1, alpha 2, up to some alpha n here. And this is now going to remove a specific state. So what we could assume now is that this alpha, this state alpha is equal to n. So when we then do the permutations here, this is going to be given by minus, and then we have n minus 1. So this is the number of permutations we have to make. And then I have an A alpha 1 dagger, A alpha 2, and then up to A alpha n minus 1 dagger acting on 0. And this one is an n minus 1 particle state. So keep in mind that these are all fermions here. So one of the things we could have done now is clearly that this is the case if this alpha is equal to one of the states in this original state. So if alpha, the state alpha, is included in this set, alpha 1, alpha 2, up to alpha n, then clearly this is non-zero. And we could now have defined this specific state. Let's now put in a labeling for that, alpha n. We could say now that this is a state which we just call C. Or, as you will see later, I'm also going to use the notation phi 0, and that's going to indicate an ansatz for normally the ground state of the system. So if you now look at the single particle states which we have, and I'm going to use this kind of alpha notation here. So we have a set of states up to the Fermi level, and then we fill them up. So we have an alpha 1, and then an alpha I, and this goes on up to alpha n. So these states are all filled up. And then we have some additional states which we have on above the Fermi level. So these states here, they define this state C, or this phi 0 as I'm going to use a little bit later. So you will often see in my notation that sometimes I use C. The C is often used for core. So you have some particles which fill up to a certain level. And in atomic physics, if you think of the neon atom, they could define a core. You put one electron on top of this core, and then you have the sodium, and so on. And then these other states, they would now begin here with an alpha n plus 1, and they go up all the way up to a limit, which we have put in here, which we can call from alpha lambda. In principle, there's an infinity of such states. Okay, so if we now look at the rules here, we know that if the state alpha, which we looked at, is not included in this set alpha 1, alpha 2, up to alpha n, what we have then is that this A alpha acting on this state C must obviously be 0, right? And else, if it is included, as we said, then this A alpha acting on C is different from 0. So if it's not included, then it's 0. If it is included, then it's different from 0. So what we will find it convenient now is actually to define a new basis set. We should also, if we now try to have A alpha dagger acting on this vacuum state C, so that will obviously be, in this case, that would be 0 if alpha is included. Alpha 1, alpha 2, up to alpha n. And else, then it's going to give us a state, which now will be given by alpha, alpha 1, alpha 2, up to alpha n. And then we have to perform the permutations, because this alpha then is a state which belongs to the states alpha n plus 1 and to infinity. So that means that this would typically be, when we reorder, we are then going to have these permutations of operators, these interchanges, and then we're going to have an A alpha 1 dagger, A alpha 2 dagger, up to A alpha n. And then we have the final state alpha, which we have left unspecified. So these are the type of operations which we can use to define a new set of operators. So that means that in this specific case, if it's not included, then we say that A alpha acting on C is different from 0. So what is common then is to define a new operator. And these are normally called quasi-particle operators. And we are going to look at some of the the operations which we're going to deal with these operators. So define a new operator. And we are going to call this operator B alpha. And this B alpha, when it acts on this vacuum state, it's going to give us 0. So keep in mind that the original one, which we had, A alpha acting on the true vacuum, was equal to 0. But now we define a new operator, and we're also going to define these operators to respect the same commutation relations which we had previously. So if we have a operator beta alpha dagger and beta beta dagger, this is going to be given by, it's going to be equal to the same relation when we have the emission conjugates. So this is going to be 0. And then I'm going to insist on the standard commutation relation as well. And this is going to give us a delta alpha beta. And the only contraction which I now am going to let be different from 0, sorry, not alpha A, but beta. This is the only, with these definitions, I'm going to have only this contraction to be 0. Okay? So all other contractions, so if I calculate the contractions B alpha dagger, B beta, that's going to be equal to B alpha as before. So there's no difference between what we had before. So these contractions are 0. So we can then just use Wick's theorem as before. Now, later, I'm going to redefine them, because now these are general operators. So what I have to do now is to decide how these operators are going to function. So I'm going now, what I want is I have a B alpha of C B alpha acting on the state C. What I want now is the following. So this is the same as this A alpha dagger acting on C. So now I add a state if alpha is above the Fermi level. Yeah.
Why is all the contractions 0? B alpha, B beta dagger. You now have 4 different contractions.
Yeah.
They're all 0.
Oh, sorry. I actually,
Yes.
I was thinking of the next line.
Yeah.
This is, I don't know if you notice that sometimes when you write, I tend to forget all the small words because you're thinking of the next word, right?
Mm.
And then it's like the determined article or whatever kind of small word you have in between is often left out because you're just into the next one.
Mm.
Yeah, I mean, I have it. I just read it off in front here, and then it's so thanks. And then we have in case it's less or below. So if alpha is smaller or equal to up to the Fermi level. We're also going to assume that this state, which we sometimes will label as a phi 0, we are going to assume that that's normalized. So we just assume that. Then we can define the Hermitian conjugate of this operator, which is simply B alpha dagger, and then it's Hermitian conjugate. So by definition there. So that means that we can now define these operators in the following way. So we would define this B alpha. We can define that as an operator A alpha when alpha is larger than F, and then A alpha dagger when alpha is less or equal than F. So the way we're going to interpret them is that if alpha is less than F, then this operator creates a hole below the Fermi level. So it's the same as knocking out a particle from the Fermi level. So it creates a hole. That's why these operators are Fodor's particle hole operators. And then I have my B alpha, which is given by A alpha dagger in case alpha is larger than the Fermi level. And then A alpha when alpha is less than the Fermi level. So this is just a redefinition of the operators. Later, we are going to make this more general in terms of unitary transformations. So we can always redefine these operators as linear combinations of other operators, or simply just redefine the way they function. And what we're going to look at now is actually the implementations of the anti-commutation rules and see that we actually get back the same physics. I mean, a transformation of your basis set or the transformation of the operators should not change the physics. So if I calculate an expectation value of, let's say, the number operator, I should get the same number of particles as I had in this formalism as I had in the other formalism. So these are just definitions. And the reason for that is that if you now look at a specific state, suppose I want to look at the state, and now we put the Fermi level here. And I have filled up my states up to the Fermi level. And now I could think of looking at one of these states being knocked out and up to a higher excited state. So when I put this black one here, that means that this state is vacated now. So there is nothing there. So you would think of this as a hole. And normally people would call these as particles. Sometimes it's a misnomer because I would think of all states below the Fermi level as particles, which are filling up to a certain level. But then the way you think of these is as these as whole states, because you're going to reinterpret everything in terms of particle hole excitations. So you can rewrite your excitations in terms of excitation with respect to a new vacuum. So you could take the original vacuum, the true vacuum, and then you could think of exciting all these particles to the different states. Or you can look at the excitation with respect to a reference state. And this is a little bit more handy because it's going to involve excitations of the type 2 particle, 2 hole, 1 particle, 1 hole. And if the interaction is only of a 2-body type, it can only act at 2 particles at a time. So if you're looking at this would be a 1 particle, 1 hole excitation. And then you can, if you take and promote 2 here, so if you promote this one up here, then this would be a 2 particle, 2 hole excitation, and so forth. Okay, so let's now look at how we can rewrite an operator in this new set of creation and annihilation operators. So let's look at the number operator, which is a pretty simple one. So the way we defined it previously was in terms of the alpha operators, the A operators, and these are operators which now relate to the true vacuum. Now, when I now look at the sum here, and I want to rewrite that in terms of the new operators, the thing I can do now is simply to rewrite this in terms of alpha larger than F, and then A alpha dagger, A alpha, plus a sum, because remember now that the sum goes from 0 and in principle to infinity. And then I have a finite sum here over the states below the Fermi level. And now I can go back to the definitions of the operators I have, and then simply put in the new definitions. But keep in mind that, as we discussed last week, we want to have these operators to be normal ordered. So that means we have the annihilation operators to the right and the creation operators to the left. So when we now rewrite this in terms of the new operators, we just look up the definitions of the operators. And now we see that if these states are above the Fermi level, this simply becomes B alpha dagger of B alpha. So if you just look up the definitions, but now when I do this, then I have to be a little bit careful because this is just going to give me a B alpha dagger here. And if I now apply this to, let's say, the vacuum state, the new vacuum state, then we know that this state alpha is already present in the vacuum state. So that means that that's going to give me automatically 0, the last term. What I can do, however, I can use the anti-commutation relations and rewrite that in terms of, so this operator here is actually given by delta alpha, alpha, minus B alpha dagger, B alpha. Okay? And you can easily see that these commutation relations, they simply follow from the definitions of the operators A, the original definition. It's not so difficult to convince yourself about that. So it means that I have a sum here, and this sum runs over all the single particle states up to the Fermi level. So if you now look at this sum alpha, and we have this Kronecker delta alpha alpha, which is just 1. So this is just a sum over all the particles which we have present in the system, and that's n. So what I get then is alpha, and then B alpha dagger, B alpha, plus this term n, number of particles, so just a constant. And then I have B alpha dagger, B alpha. And now the operators are normal ordered. So I always want to have operators in a normal ordered form, because then I can plug them immediately into Wick's generalized theorem, where it says that if you have chains of strings of normal order operators, you don't need to take any contractions with the operators within the same chain. Because, you know, if I take this contraction here now, that is automatically 0, right? So that's a nice thing of having something normal ordered. Now, let's now calculate a specific expectation value. And what I'm going to do now is to, instead of having this definition, which you see here with alpha larger than F and alpha smaller or less than F, I'm now going to introduce a notation which is widely used in many-body physics. And in particular, for those of you coming from quantum chemistry, you're going to see this notation here. So let me just introduce that. So instead of rewriting this every time, I'm going to use letters which are going to identify states above the Fermi level and below the Fermi level. So let's call this definition, or rather, this is better called labeling of states. And I'm going to try to use this throughout the rest of the course here of single particle states. And the way we're going to do that is, so we go back to the states which we had. So we had this infinity of states above the Fermi level. So here we have the Fermi level, and then we have all states below the Fermi level. So we are going to give a generic labeling for the states for all states in terms of letter P, Q, R, S, etc. And normally it's very seldom we go beyond a free body interaction. So even though this sounds like a strange usage of the alphabet, we will never need more than 3 to 4 pairs of such letters. So that means that we are going to use the letters I, J, K, L for states below the Fermi level. And then we are going to have letters A, B, C, D, and obviously less than I, J, K, L, essentially because it's very seldom we are going to look at operators which include more. And if we have more, then we have to change the labeling. Okay? So that means that we are going to rewrite that's number operator as an N, which now goes like a sum of A, and then I have a BA dagger, BA minus, and then I have a BI here, sum of I, plus this term N, the number of particles. So let's now look at some expectation values and just get some feeling. So what I said is that we defined the reference state. So that means all the level being filled up to the Fermi level. We also call this phi 0. Now, what I'm going to do now is when I act on this state here with a creation operator of the type. So let me just, no, not that one. So if I now take B of A dagger, acting on phi 0, this is actually the same as A of A dagger, because this is now uniquely specified as a state above the Fermi level. So I just wanted to introduce these notations here, and I'm going to label this state with a phi of A up here. So to indicate that now I have added a particle to the reference state. So these are just notations, right? So remember now that A is uniquely defined as a state above the Fermi level. So if you go back to the definitions which we had for these operators, it means that when, like here, when alpha is larger than F, then it's simply replaced by a standard creation operator. Then I'm going to introduce a new state here. So if I have a BI acting on phi 0, this is the same as the old AI destroying a state below the Fermi level. And I is included in the states below the Fermi level. And this is something you would label as an I here. So this is an N-1 state. This is obviously an N+1 state. Then what I can do next, I can now create a one particle, one hole state. So that would be a new Slater determinant where I take this reference state. So I take a BA dagger of B of I dagger acting on this phi 0. And that's the same as A, and you're going to see now, later, I'm actually going to go back to the old operators, but I'm going to have a unique labeling on the single particle states. So that means that we have then to be a little bit careful with the way we define the contractions. So I'm going to bring back at the end, instead of using these operators B and so on, I'm actually going to go back to the original operators. But then I have to be a little bit careful with the definition of the contractions. And that's the only thing to take care of. And then I would have an A of I acting on this state here. And the kind of compact notation which I'm going to use is a notation which goes like this now. So I have an I here and an A here. And we read this as a one particle, one hole excitation. So these are just definitions which we need to set up now. The next thing I need to look at is let's assume now that we take a state where we have let's say we create two particles, B of B, and then we have a B of J, of B of I, dagger. So I create a hole with state J and a state I, and same, I create a particle with in a state A and a state B, acting on this phi 0. So this is the same as in the old notation. And then I have an AJ of AI acting on the same state. And we're going to use a compact notation for that, which goes like, and you won't be surprised if I write it like this, of AB. And this is what we will call a two-particle, two-hole excitation. So one of the differences between first quantization and second quantization, in second quantization, you let the particles interact infinitely many times. In second quantization, since you have taken away the standard coordinate space representation, you're letting the system go through an infinity of particle hole excitations. So if you have 10 particles, you can make 10 particle, 10 hole excitations. And since your basis states, the single particle basis states, is an infinite basis, you have an infinity of 10 particle, 10 hole excitations. You have an infinity of 2 particle, 2 hole excitations, and so on. So in order to be able to calculate, you need to make a truncation. And this is going to be our first many-body method when we come to full configuration interaction theory. Any questions so far? So let's now do some calculations here and see what we get. So if I now calculate, suppose I take the expectation value of this quantity here. So I have a one particle, one hole state. So without having done any calculation, what should we get? If you now assume that this has n particles, what should we get as an expectation value here? N, exactly. So even if we now have changed the form here, we should actually get that. So changing the operators doesn't mean that, it shouldn't change the physics. And so if we now take and write it out, so what we have then, so we would have a C here, and now I'm just putting in this new operator. So what I'm going to get is a B of I times a B of A, and I and A are different by definition. Then, since I now have used A, so this is a specific state defined by A and I. So I've just singled out one possible Slater determinant. And that's why I need to put a B here to indicate that this can be any of the single particle states above the Fermi level. So I should get a B of B here, dagger, B of B minus, and then I have this sum over J, and then I have my BJ, dagger, BJ. So this is the operator plus N, which is just a constant. So I'm just plugging in the form of the operator now. And this is multiplied with B of A dagger, B of I dagger, and this takes C again. So I'm gonna, sometimes I use C because if I'm lazy, it's easier to write C than phi 0. Okay, then what we need to look at now are the contractions. So we would have a set of contractions here. So let's take the BI, BA, and then we take BB and BB here. So there is a sum here over B. So just let us take this term here. And now due to the definitions, we have only one possibilities for the I's. So remember now that the B's, these are larger than F. So if I try to make a contraction here, that's automatically 0, because I have put in labels where I say that this is state above the Fermi level, I is 1 below, so they can never be equal. So the Kronecker delta gives 0. So the only Kronecker deltas which are different from 0 here would be this one with itself. So that's a bystanding whole state now. So this is the only one which matches. This and that one is 0. This and this one is different from 0. This and this one is going to be different from 0. But if I take this one with that one, that's 0. So the only contractions here which gives something which is non-zero is actually this one. So, and then what I get is this contraction, and then I have this contraction. Remember also that I'm using Wick's generalized theorem. So I have strings of operator, and I cannot make, so I'm just indicating this. These are the general strings of operators which I have. So I cannot take contractions within the same normal ordered string of operators. That gives automatically 0 because it's normal ordered. So that term is simply going to give me delta AB multiplied with delta II, which I'm just leaving out. Then I have a new term. So I have a minus, and then I'm getting this sum over the J's, and I still have my BI, BA, and then I have my BJ dagger, BJ, and then I have my BA dagger of B of I. So in this case, again, the only contractions which are possible in our case is actually this contraction here. And then I have this contraction here. And clearly, since A is different from I and J, by the specific definition we have done, this is the only contraction which comes in here. So this gives me a minus delta ij. So from the sum, it just singles out one term. And I have 1 minus 1. And now I'm getting a new term, which is plus n. And then I need to take the contractions between BI, BA, and then BA dagger, BI. And the only possibilities here are these possibilities here. So 1 minus 1 plus n gives me n. Okay. Is that, everybody sees that? So, yeah.
Would it be much more, many more possibilities for delta ij? And would it be many more possibilities for delta ij than delta nb?
No, because the, so if this one and that one?
No, I was thinking of the delta term. There, the ij isn't, are they?
This?
They are known for them. I was thinking about the one.
The one above? So yeah, this one, and then I have this one. But
yeah, I
but
was thinking, are there more possible excited states?
oh, there are many, but we have fixed A, so that's just fixed to one specific state.
Okay.
So what I did now is I constructed a determinant here, which has where I just removed one specific one. But then clearly, what you could say then is that if this is a very good question, because what you could say now is that you would have a whole set, the number of these operators would then be a sum, or these states would be a sum of all this IA here. But now I'm just looking at one specific one. So later we're actually going to use this notation here when we are looking at the FCI, the derivation of the FCI method. But now we just nailed it down and said it's in this specific state. We just picked one Slater determinant. And clearly, if you then do the ground state to ground state, you would then just get n, the number of particles. So the number of particles is conserved. So we made a transformation. But the thing we should notice is that the only contraction here, which is different from zero, only different from zero contraction, is this B, and now I'm putting these general labels, Q. So this is a general state. We haven't specified whether this is below or above the Fermi level. This is the only one which is different from zero, in case P is equal to Q. Now, what we could have done is actually to rewrite this in a slightly more compact form. So if you take out the additional term N, if you now look at the terms which we have A or B alpha, BA minus a sum over J, where we now explicitly single out all states and particle states. So can we write this in a more compact form, where we can, in a way, introduce the old creation and annihilation operators? So if you now think of the kind of expectation values, so let me just use this C. If I take this one, A dagger, AA on C, if you look at this one, so this is what we would now call the contraction of these with the new vacuum state. What should we have here? Because just keep in mind that A is not included in C. Okay, this is a state above the Fermi level. So what should we have here for that specific contraction? That should be zero, right? So if we, however, we have to be a little bit careful now. So if I look at the following, I take, just let's look at this one, just remind ourselves of that. So if I do this one, this is not equal to zero. I could just put a general one B here. So this would be the contraction of AB, and this is delta AB. So this is different from zero when it acts on a true vacuum. And if I do that here again, if I take zero and AB, and this operator here, sorry, not that one. This is A of A dagger, A of B, and that's automatically zero by definition. So for that operator, things are okay. If I also look at this new here, so this is zero. C is now the new vacuum state. And if I take AB, A dagger on C, which I would then write in this compact form, AB, A dagger, like that, that is also different from zero. Because these are now states above the Fermi level. So I create a new one and make an n+1 state, and then I take it away if B is equal to A. And then I'm back to an n state. So that should also be a delta alpha beta, a delta alpha B. Then I can repeat the same now with the states below the Fermi level. So one thing which we have, so if I also go back to these operators, which I introduced, this B of A of B. These operators, they are now, this is different from 0. So this is given by BA of BB dagger, delta AB. Then, if I look back at the definition which I made of this minus C, if I now take the number operator. So in the number operator, I have a minus sign here. So there is a BI, BJ dagger of C. So this is with the new operators. And then this is something which we would write as minus BI, BJ with the new operators. And that's given by minus delta IJ. If I plug in the original operators, this should be minus C. And then I have AI dagger, AJ of C. So that means that what I need now is to modify my definition of the contraction if I want to use the operators which we started with. So this should be actually minus delta IJ. So what we end up with now is the following. So if I collect one, if I take away the minus sign, so I can say now that AI, AJ is equal to delta IJ if I and J are below the Fermi level. And I write it like this. So I need to modify my contraction rule if I want to revert back to the traditional operators. And then I'm going to take away the minus sign here. And then I will have an A dagger, AB. And the only contraction which is different from 0 is actually this one, if A and B are larger than F. So what I'm going to do now, after the break, I'm sorry if I go a little bit over time, I'm going to go back to the operators which we started with. And that means that I'm going to redefine this part here in terms of the other operators. And I'm going to label that as a new type of normal ordered operator, because I don't want to run with these B operators and the definitions of states below and above. So I'm just going to recognize states above and below by these letters I and J and A and B. So I'm going to put the recording on pause. So with these definitions, what we can do now is to rewrite this operator which we put up in the new set of creation and annihilation operators and go back to the old form. So we had this specific definition of the operator, B of I, BI, dagger. So this is a normal ordered operator, plus just the number of particles which we have, which is just a constant. And that refers to how many particles we have in the reference state. And I'm just going to rewrite this in terms of a general operator, a general state P. So this can be states below and above the Fermi level. And I'm going to use a notation here, which at the end, I'm going to drop anyway. But this is just to indicate that these operators are normal ordered with respect to the new vacuum state. And you will see this kind of notation. Some textbooks, I think some textbooks use the colon sign. So this is just to indicate that this is now a normal ordered operator, which actually reads like this. And we're now run over all the given particle states, all possible particle states, plus n. So I have to be a little bit careful. So these curly brackets refer to the fact that I'm now normal ordering things with respect to a new vacuum state. And I have the contraction rules, which now simply say that this is equal to delta PQ if P and Q are above the Fermi level. And then I have AP dagger, AQ which is given again by equal to the Kronecker delta, delta PQ, if P and Q are below the Fermi level. So when we're now going to do the contractions, let's now take a look at what this would look like if we go back to the same example which we had before. So before we looked at a case where we had a one particle, one hole state. So we had this specific state here, and then we have a state A, creation operator AI, and this is acting on the state C, as we called it, or this phi 0. So let's look at the expectation value again, but now with the new normal ordered operator with respect to the new vacuum. So this is going to be equal to, so I'm going to have a state C, I have my A of I, and this now becomes equal to AI dagger because I'm taking the Hermitian conjugate. And this is now multiplied with the sum of a P of an AP dagger AP plus N. And this is again multiplied with AI of AA and AI, like that. So let's look at the contractions now. So what we have, let's only take those. So we have three normal ordered operators. Like this. Now, depending on the kind of contractions which we take, if we go back and look at the rules which we put up, so we have this possibility here and this possibility. So this should be an A of A. Because if I try to contract P with this one, that is equal to 0. If I contract P with this state, that means that P is equal to I. But then I would have to take the contractions between this one and that one. That's fully possible. So that's another contraction which I can take. But if I fix A with P, then I cannot have I with P here. So that means that my state A of I has to go here. And we know that that is different from 0, right? Because if these are states below the Fermi level, as we defined here, then this is a okay contraction with the definitions which we have made. Then we see now that this term here gives us simply delta P of A and delta II. And if I look at the sum, this is going to pick out only one element. So that gives us just 1. Nothing more than that. Okay? Then I have a new contraction here. So I have an A of I, AA. That's the only other possible one of AI and AI. So in this specific case, I'm going to let this contract with that one. But now the only contractions which are non-zero is this one with that. And now you remember that when we had such crossing lines, when we looked at the contraction, that gives rise to a minus sign. So this gives us minus delta of PI multiplied with delta AA. And when I go back to the sum, that simply gives me minus 1. So I have 1 minus 1. And then I have a final term, which is this constant. And this is multiplied with AI dagger AI, AAA, and too many A's here, right? Like that. And the only possibilities which we have here is this one and that one. And that gives us simply N. So when I bring everything back, I have N, which is what I should have. So what you see now, with this definition which I have, I haven't written this out in terms of a negative sign here, because using these contraction rules, which you have, then the negative sign here pops out automagically from the setup of the contractions. And we have now said that this contraction here with P is different from 0 because this is a state below the Fermi level. So this is with respect to the new vacuum, that this contraction is non-zero, only with respect to the new vacuum. Because if we were to take the 0 vacuum, this would be automatically equal to 0. Okay, so let's now look at the new operator. And since we're getting a little bit excited now, so let's look at H0. And H0, the way we wrote it out was a sum of alpha and beta. And then we had the matrix element, alpha, H0 to beta. And then we had the creation operator and the annihilation operator. This was the operator, the way we wrote it before. Now, what we can do now is simply to rewrite this in terms of the operators B. So what I'm going to do now is to give you a kind of boring exercise of just rewriting the sum. So we can have now a sum over alpha, beta, larger than F, obviously, like we did before with the number operator. So this would have the same element here, but now we could replace this with a B alpha, and then we will get a B beta here. So what I'm doing now, I'm just going back to the definition of these operators B in terms of the original operators A, and now I'm just plugging them in here. So then when I look at it, I have two terms. So I have to look at the case where alpha is larger than F and beta is less than F. So that's going to give me a term where I now, when I just plug in the operators, then I'm going to get a B alpha dagger. But since this beta is a whole state, this becomes a B beta dagger. Then I'm getting a new term here where I have alpha less than F and beta larger than F. And then I'm going to have an alpha H0 of beta. And then I'm going to have a B alpha, B beta. Now I can rewrite the last term with the same summation limits as the first one. So what I'm going to do then is just to interchange, because these are just dummies, right? Dummy variables. So I can just call them whatever I want. So if you interchange, then I will have the last term, let me just write it out, is going to have the same summation limits as the previous one with respect to beta and alpha. And then I'm simply going to get beta, H0 alpha, and there's going to be still a normal ordered operator, B beta, B of alpha. And then I have a final term where I now have the terms plus alpha beta less than the Fermi level. And then I have my alpha H0 of beta. And then I have a B alpha, B beta, like this. Now, this is not normal ordered. So actually, I want to bring it back in a normal ordered form. So what I do then, I simply replace it with the commutation relations, delta alpha beta minus B beta dagger, B alpha. Now I can reorder everything, and I want to have this in an order where I interchange. In the last term, I'm going to interchange beta and alpha, just to have a sum which runs over alpha and beta, and then the operator goes like beta alpha, beta dagger, B dagger, alpha, and B beta. So I can rewrite this now in terms of the following expression. So I have an alpha beta larger than F, and then I have an alpha H0 of beta, and then I have a B alpha B beta. This is not very exciting actually. So let me just rewrite it so you can see everything more clearly. And then I have a plus, I have a sum over alpha larger than F, beta less than equal than F, and then I have a alpha H0 of beta, of B alpha, B beta. So this is normal order. And then in the next one, I interchanged beta and alpha. So I get a B beta and a B alpha plus, and I have a Kronecker delta. So that means that what I'm doing now is I'm summing over alpha less than f. I have a diagonal matrix element, H0 of alpha, like this. And we remember that term. If alpha is an eigenbasis of H0, we could actually replace that with the epsilon alphas, if alpha is an eigenbasis for H0. So we see that we gain back that term which we calculated in the very beginning of the semester when we took the expectation value, the ground state of the ground state for the H0 operator. And this is going to redefine. So if you look at this term here, this looks like very much what we got with the number operator, where we had this term here. So we just get a constant, which is now the sum of the single particle energies from the vacuum state. But then we have an additional term. And that additional term goes like minus, and I have an alpha beta less than f. And then I have my beta now. I've interchanged because I want to have it in a form where the operator looks like this. These are just dummy variables. Then I have this last term here. Now, if I now want to calculate the expectation value of the same quantity, which we suppose we want to calculate the expectation value of the ground state to the ground state. So let's look at examples now. Later, we are going to rewrite this in terms of the old operators. And then we are going to get a much more compact form. And you will see that you can actually rewrite all these operators here in the way we did with the number operator. But let's now look at an example. And suppose we want to calculate phi 0 of H0 with phi 0. So what I'm going to do now is simply just to set up the contractions which we are going to do. So there's going to be one set of contractions. So what we are going to have now is this, I'm going to call this C, and then I have an A alpha, a B alpha, B beta of C. And this is going to be for states above the Fermi level. And you can see what this has to be because we decided that this contraction is equal to 0 because we are trying to annihilate a state which doesn't exist. So this is equal to 0. And what you will see when you do the contractions here is that this state which you have here is the same because we are, with this one, we are going to get exactly equal to 0 because here we have a contraction of this type and that's defined to be 0. We have a contraction of this type, which is defined to be 0. We have a contraction of this type, which is defined to be 0. And the only term which survives is actually this one. So when I do that, I'm going to simply set up plus plus 0 plus 0 and plus the final term, which is just the sum over the epsilon alphas. And where we have assumed now that H0 acting on alpha is equal to epsilon alpha times alpha, the state alpha. So this is what we had before. And that's the only term which survives here. Then, if we want to be a little bit more ambitious, we can actually calculate the new operator, the state which we had, the one particle, one whole state, and just go through the calculations with that. So let's try that. So let's now look at the next example. And we calculate now the expectation value of H0 with a specific state, AI. So this is a one particle, one whole state, like that. And what we need is the following now. So remember now that in these operators, this will now be written. So this state, I'm actually going to define a general state in order to avoid a mess up with notation. So I'm going to define a state KC. This is K and C are fixed now. So these are given in with these set of operators by BC or BK. It's a whole operator acting on the vacuum state C. So what I need now is a set of such operations where I need to perform the contractions. So I will get the following contractions. So I'm going to have the BK, BC, and this acts on the vacuum state here. And then I have a B alpha, B beta, where alpha and beta are larger than F. And then I have B of this state C and B of K dagger 0. So vacuum state C. So this is the first term in this operator. And what I'm doing now, it's a little bit sloppy notation because I'm leaving out the specific matrix elements. And I'm just going to collect them afterwards. Now, if you look at this specific term here, the only possibilities which we have, since C is obviously different from K, is this possibility here and that one. Because we have defined by definition that some of these, there's only one set of contractions which are possible. So this is a possible contraction. This is also a possible contraction. And remember now that alpha and beta are above the Fermi level. So if I try to make a contraction with beta and K, this has to be 0 because K is below the Fermi level. So that means that in this specific case, this is the only contraction. These are the only contractions which are possible. So this gives me delta KK, which is obvious. I have a delta C alpha and a delta beta C. So the double sum which I have over alpha and beta, that gives me one single term, which is epsilon C. Okay. Then let's look at the next terms here. So we have terms of the type BK, BC, but then they have the operator. If we now go back, the way we wrote out the operator, we have two creation operators and two annihilation operators here. So we would have a beta alpha dagger and beta beta dagger, where alpha is above the Fermi level and beta is below the Fermi level. And then I have to multiply this with BC dagger and BK dagger. So you see now that if you look at the contractions here, I have 4 creation operators and 2 annihilation operators. So that's 0. And then if you go back to the operators which you have here, that's pretty obvious. You have 2 annihilation operators. So you're going to get 4 annihilation operators and 2 creation operators. And to get something which is different from 0, you need always to have an equal number of creation and annihilation operators. So this gives automatically 0. Then we have to evaluate this term, and that's pretty obvious. That's just going to give us this sum of epsilon alphas. And then finally, we need to look at this term. So let's look at the final term here. So that's going to give us a minus, and then we have a C, and then I have this BK, BC, and now I have this B alpha, B beta, and then BC or BK. And in this case, alpha and beta are below the Fermi level. So that means that contractions which I take between beta and C have to be 0. And C and alpha have to be 0. So the only contractions which now are possible are the contractions where I let C go to C, and then I have to have beta and like this. And that's going to give us a Kronecker delta of K with alpha and delta K with beta plus delta C of C. And that leads to minus epsilon K. And then I have the constant term, the normal order term. Oh no, so what I'm going to do now is actually to label this term here. This specific sum is something which I'm going to call with an uppercase epsilon, and I'm going to call this epsilon 0. So what you get now is that this expectation value of a specific state with K and C with H0 gives us a 5K of C. It's going to give us this energy here. And then it's going to give us an epsilon C minus an epsilon K. So that means that I have a difference between the two single particle states for a hole and the particle, plus the constant term, which comes from the core and what we call the core energy normal. Okay, or just a reference energy. You can try now another example. Suppose you take a KL, so you have a two-particle, two-hole state. So I'm just going to set up the answer here, but this is also going to be pretty obvious. So if you want to try it, what you're going to see then is that this is going to be given by epsilon 0 again, and then you're going to have epsilon C plus epsilon D minus epsilon K minus epsilon L. This is going to play an important role when we are going to do many-body perturbation theory or copper cluster theory or any of the approximative methods which we're going to look at. So just keep these kind of relations in mind here. But what we are going to do now is to redefine this operator in terms of this new normal order product. So I'm going to rewrite it in terms of a sum of a P of Q, which is unspecified. It runs over all the single particle states of H0 of Q. And then I have this new normal order product of AP with respect to the new vacuum state, plus this constant term epsilon 0. So this is my new normal ordered one-body operator with respect to the new vacuum state. And the only difference you see here from the number operator, so if you look at the number operator, what we had then is a P of Q, and then I had no matrix element here, but I had just the normal ordered operator, AP dagger, AQ, plus a contribution from the reference state or the new vacuum state, which was a number of particles. So this kind of constant which you see here comes from the same expectation value as you had for the number operator. Now, one thing which we can do now is actually to recalculate the expectation value which we had previously. And now we're going to look at the one particle, one hole state. So let's recalculate it. So we have a state, one particle, one hole state, I and A. And we take this operator now in the new normal ordered scheme. So this is going to now contain a sum over P and Q. I have my vacuum state and I have my AI dagger, AA. And then I have this normal ordered operator, AP, and I skip these curly brackets because now I'm assuming that this is normal ordered with respect to the new vacuum. And then I have an A dagger and then an AI acting on C, multiplied with the matrix elements P of H0 of Q. So that's one term. And then the next term is actually just a constant term, which we put up, this epsilon 0. And then what I have is a C with an AI, A dagger, AI, C. So if you look at the last term, the only contractions which are possible are these two here. So remember now that the I's are states below the Fermi level, and that means that for them, the contraction which is different from 0 is the one where I have an A dagger to A. So the final term gives me just epsilon 0. So this gives up delta I, and delta AA. Then I have to look at the term which we have here. So let's take a closer look at these terms. So I have an AI dagger, AA, AP, So now I'm just looking at the contractions. So in this case, I mean, if I do this, then this is locked. So that is non-zero. So that gives me a delta I here. Then, if I take the only possible contractions now, using Wick's generalized theorem and the definition of the contractions with respect to the new vacuum, then this gives me a delta QA, and this gives me a delta AP. If I go back to the sum here, the double sum vanishes due to the Kronecker deltas. So this gives me a contribution, which is simply epsilon A, the energy of the single particle state above the Fermi level. Then I have the next one. I have AI, AA, AP dagger, AQ of AA dagger, AI. So if I now lock my particle state here, so remember again that you have strings of normal order operators. You see now that the only possibilities I have is this one going to that, and then this one going to that. And due to the crossing lines, we have interchanges of operators here, which means we get a minus sign when we place the operators in the right positions. So this simply leaves us with minus I here. So when I look at the final expectation value, then I have an AI's and one particle, one whole state. Then I have an I, and this is simply epsilon 0 plus epsilon A minus epsilon I. So when we are going to set up the Hamiltonian matrix to diagonalize and do full configuration interaction theory, we're going to use this notation here. And then you can really read off what the matrix elements like here along the diagonal are going to look like. So that's it's a very compact way of doing many-body physics here. Now, one thing which you will hate me forever for if I were to do that is actually to go through the derivation of the two-body operator, because then I have a 4 double sum. And I would then have to look at all the combinations. So what I'm going to do now is simply to set up the expression form. And I have an exercise. It's not the most exciting thing, but you saw the way I did it for the one-body operator, where I rewrote the limits, and then you can rewrite it in terms of the operators. But the two-body operator is actually, when you write it in this new normal ordered way, you're going to get a term which goes like PQ. It's actually in the lecture notes. You will actually find the expressions in terms of the particle whole creation and annihilation operators. But I'm going to just give you the general expression here. So we would have factor 1/4, and we used anti-symmetrized matrix elements of RS. So this is an operators, anti-symmetrized. And then we have an AP dagger. So we have this notation that this is normal ordered with respect to the new vacuum. And this is AS, AR. But then I have two additional terms. And these terms become very important now when we are going to look at for example, Hartree-Fock theory. Because Hartree-Fock theory is always defined with respect to a given reference state. So it's not so difficult actually to derive these equations. So I'm going to get a sum of PQ, but then I'm going to have an I here. So there's going to be an explicit state below the Fermi level. And then I have a Q of I. And this is multiplied with this normal ordered operator. Actually, all the derivations are in the notes. But then I have a constant term. And the constant term is the same which we calculated when we, in the beginning of the semester, when we looked at a general Slater determinant, the expectational value of that one with a two-body interaction. And that's simply given by 1 sum of ij, states below the Fermi level. So this is just a constant. Bij, anti-symmetrized. So this way of rewriting your Hamiltonian means that what we are going to get now is a much more compact way of rewriting things. So we have an H0 plus H of I with respect to the new vacuum. So we are going to define something which I will call reference energy, which is the same as phi 0, the ground state, ansatz of H. And this is something we calculated in the beginning. This is given by this epsilon 0 plus this term 1/2 of ij, and this has no creation and annihilation operators with respect to the new vacuum. So in the beginning of the semester, we actually calculated such a quantity. And that included a double sum over the single particle states below the Fermi-level. And this defines the reference energy. Now, these states which you have, they can be optimized single particle states, where you, for instance, have run a Hartree-Fock calculation or density functional theory calculations. And this is something you don't need to deal with. You just add it to the total energy. And then the remaining parts, which lead to what we are going to call the correlation energy, will be defined by these new normal ordered operators. So this is one piece. And then when we now look at the operator which we have, so let me just bring up that one. I'm going to define a new set of matrix elements. And these are going to be P of an operator F of Q. And that's going to be given by this sum over I, which we had. And it has P of I, of V, Q of I. So these are just the matrix elements which I'm defining here, plus this P of H0 of Q. Sometimes these basis sets, P and Q, can be eigenstates of H0. Or if we have run a Hartree-Fock calculation, they will be eigenstates of this operator F. So if I use these definitions here, I can actually rewrite H in terms of the following operators. So I'm going to have a 1/4 and the sum which runs freely over all the single particle states, but normal ordered with respect to the new vacuum. So I have an AP dagger, AQ dagger, AS, AR. Next, what I'm going to get now, if you now look at what I have defined here, if you look at this definition here and that one. So I have this P, if you look at the one-body operator, I would have in the one-body operator, I have a term like this. Actually, this term here, as you can see, as a one-body term here. Now, if I go at the way I rewrote the two-body operator, it has also a similar term. Now, if I now look at the sum of a P and Q and look at this definition of the operator which I plugged in, this operator or this operator F, then it contains this term and that term. So I can actually rewrite that in terms of a sum of a P and Q. And then I have this matrix elements here multiplied with a one-body term plus E0 reference, which is just a constant. So when I'm now calculating expectation values, what I need to do is simply to evaluate expectation values for these terms, or if I'm looking at transition matrix elements, I'm just going to evaluate matrix elements between Slater determinants and Slater determinants. And the whole thing now is that we have a much more compact way of defining the Hamiltonian with respect to a given vacuum state. If I add a free-body Hamiltonian, this complicates life. There will be terms with the free-body operators, and then you will have a free-body operator contribution to the two-body operators, and so on. But we are mainly going to look at two-body operators in this course here. So what we can do next now is to look at some simple examples. And the easiest one is to go back to the one which we looked at. So we have the one particle, one whole state. So let's calculate this one again, of H of phi I of A. Now, we've already done H0, right? So we don't need to do H0 again. And we know that the E0 ref is just a constant. So that's just going to give us a constant again. Right? So the only thing we actually need to look at now is this term which you see here. We know how to calculate this term. So that's actually going to just give us the expectation value of this term here. So we have already done this, but we have to be a little bit careful with the matrix elements which you get here. So when I take the operators, what I'm going to have, so let's take a closer look at it. So I'm going to have to evaluate this over PQRS, and then I have my state AI dagger AA, and then I have my operator AP dagger AQ dagger AS AR, and A dagger AI. And this is multiplied with the matrix element PQVRS multiplied with a factor of 1/4, and this is anti-symmetrized. So if you now look at the contractions here, you see immediately that this has to be equal to 0. And the reason for that is that if you look at this one, if I contract that with that, so remember again that you can only link contractions with different strings of normal ordered operators. So if I have this one with that one, I could take this one with that, which is also non-zero. But I would also have, since this is a state which is a one particle, one whole state, there will always be two operators here, one creation and annihilation operators, which you cannot contract. So this specific state here, this one particle, one whole state, receives 0 contribution from this two-body form. So you can easily convince yourself that this is actually, if you try it, is equal to 0. But then you're going to get a term which runs over P and Q, which has these matrix elements P of F of Q, and that's going to contain the one body and the two-body operator. And this is something which we calculated when we looked at H0. So we have an A of I, A P dagger, AQ, and A dagger, AI of C. And here we have two possibilities. So we have this possibility and that with this one. And then we had the other one where we take the whole states, which then get contracted with the, so we have a particle state here, which goes over there. And then we have the whole state over there. So this is going to give us, and then we have, in addition, we have this reference energy, which is just the constant here. So this will give us, when we put everything together, we will have a state which looks like A of F of I. No, sorry, it's A minus I F I plus the reference energy. And then we have to look up the matrix elements F. And these matrix elements of F contain information about the two-body interaction as well. And then if you feel a challenge for tomorrow, we can actually look at same operator, but now with a state ij, AB of H and ij, AB. And that's where I'm going to stop today. And tomorrow we are going to look at a graphical representation of this, which becomes more compact when we deal with the new vacuum state. And then if we get time to it, we're going to practice a little bit and look at also some of the exercises. And then I'm going to talk about something which is called the Jordan-Wigner transformation, where you can actually transform the creation and annihilation operators in terms of Pauli matrices. And that's the way you would typically represent the Hamiltonian when you're dealing with quantum computing. And next week, we are going to start with a full configuration interaction theory, and we're going to use this notation to rewrite the way we classify or we label the Slater determinants. And then we're going to set up a Hamiltonian matrix, which we can diagonalize. And that's going to be our first real many-body method. Okay, I'm going to stop the recording.